going to share my screen. Can you see my presentation now?
Yes.
Nice. So I guess we get started. And thanks, Karim, for the introduction. And thanks, everyone, for being here. Yes, this is a continuation for your learnings on on Web3 development, smart contract building. And I think a good segue into what you already know about Solidity is creating zk applications. So that's what I'm going to do today. And just for myself, my name is um, Ahmed, and I work at DevRel at Scroll. So what I do is help developers building and having like a good experience building on Scroll. So yeah, you're all invited to start doing your application on Scroll, deploying them. As you may know, Scroll is a layer 2, so it serves for scaling Ethereum. Ethereum is also scaling now, it's becoming faster and cheaper, but layer 2s can help Ethereum become even more faster and even more cheaper. So, and without sacrificing security. So that's what Scroll is. And as what we're going to do today, we're going to first going to go into a fundamentals about what is zk, and we are going to build a circuit. We're going to learn also what a circuit is, and we're going to just do like we're going to do or review two applications. One is the most simple application, a hello world application, just to get started, to understand what is zk, what is a circuit, and to match what you already know about Ethereum development. And then we're going to review a more advanced applications, and we're going to do a private voting application. And we're going to review the architecture. We're going to go in depth into what is needed to know to create a circuit that is able to handle privacy voting and many other things. And we're going to just build it and see like how it works. I have like a working demo right now, and that I want to show to you guys. Also, if you have any questions, let me know. And even there are no like two beginner questions, because this is a very new technology, and don't be afraid to ask anything, even if you feel if it's too simple of a question. I don't think like that will be the case, because you remember like zk is super new, and it's a new way of creating things. So yeah, don't feel free to ask. Also, don't feel afraid to ask something that you think it's too advanced. Even if I am not able to answer it, I can go back into the either the protocol team or the zk team at Scroll. They are super helpful, and they can help us answer any question that you have. Okay, so let's get started. Oh, before getting started, Scroll is going through Scroll Campus right now. So if you are building an application, or if you want to start building an application and you want to launch it, you want to have users, if you want to build a successful application or product on Scroll, so the best way for you to get started is to go to open.scroll.io. And so what Scroll is doing these patches of Scroll Campus, we call them. So you can apply to to be part of the campus, and if you get selected, you will go like to join like an in-person, like like you can call it like, yeah, it's like it's a campus where you will meet other builders, and you will receive help in whatever area you need the most for building your own application. So yeah, feel free to yeah, also let me know if you have any questions about Scroll Open, how to apply, when to apply. Right now we're going to a second season for the campus, so yeah, it would be nice if you make it there. So yeah, let me know if you have any question about it. And also, like, of course, if you are wondering, okay, what kind of application can I build on Scroll? Of course, it can be like a zk application. I think it's a good it's a it there are, like, of course, on Scroll you can build games, you can build social applications, you can build DeFi applications, many things. But of course, you can also like look into zk to add something new, something that hasn't been built before. Okay, so what is zk? Let's start with the fundamentals. So zk, you can summarize it into something like this: prove something without revealing all information. So that's the privacy aspect. So this can lead to two types of zk applications that you can build today. One is privacy application, and the other one is scaling applications. So we already have a few first applications built with privacy and scaling on Ethereum. So on the privacy, I have here a couple of examples. On the privacy applications, we have, for example, Macy. Macy it's a voting application, where a secret voting applications. So you can we have done, like, I'm from Latin America, I'm from Honduras, and here in Honduras we have organized a couple of like voting rounds um, with yeah, just we distributed some funds with quadratic fundings to different like initiatives or public good funding, and we did it with privacy enabled. Did we do it? So basically, you can vote for different projects and for which you think are the best, but you won't reveal you just know like the list of voters, but you don't know which voter did which vote. So that's very good because you can it's very hard to collude in the system. And the cool thing about Macy is that, for example, if someone just asks you to vote for something just in front of your computer, just go and vote for this account. uh, Later you can change your vote, and that will be private too. So yeah, there is like a lot of like mechanics involved. I think this is very interesting. It's not the only project, of course. We also have Tornado Cash. Tornado Cash, of course, was banned in the US for some time. Now the with the new administration of the US, it's not banned anymore, and yeah, people are free to use it anymore. The Tornado Cash is a mixer that allows you to like very safely like hold, that if you hold funds on Ethereum right now and someone links an address to you, they will know exactly how much fund you have and what are you spending them on. That's not safe, and we need privacy for this, so we can have mixers. Of course, mixers is not the only thing, not privacy. We also have like social applications. So we have, I think this is called Anoncast. In Anoncast, you can only if you hold a token, only for token holders can post there. But when you post, no one, even the developers, no one can know what the developers, what the who the user is. They just know that he's one of the holders, token holders, but you don't know which one. And yeah, this is very interesting because you can also do moderation. The same with Tornado Cash. So there are many jurisdictions right now thinking about, okay, should we allow or not? How do we make people be compliant with these technologies? zk is so so expressive, and we're going to see how you can express all of these privacy features into your applications. So zk is so expressive that you can actually build and make it work in different regulations with different requirements, even preserving privacy. So yeah, I think it's super interesting what you can do in zk. We are going to focus on privacy applications for this workshop, but just so you know, that's not the only use case. The other use case is scaling. So This is mainly used on layer twos because what zk allows is that you can, yeah, basically like you can think of like compressing transactions and storing them on a layer one. So as you may know, Ethereum has been historically a bit expensive compared to other layer ones because it's the most widely used and the preferred layer one. So the cost will go up. So we build scaling applications so we can like build a lot of have a, like bundle a lot of transactions in a parallel blockchain and then store them safely and verify them on Ethereum the layer one. So that's why like Scroll is one of those. It's not the only one, but yeah, this is another use case. We are not going to cover scaling applications using zk on this workshop because there is a lot of architecture needed, a lot of you need to think about networking. It's a very like big project. So and I think that if you're interested in this is also a good area for exploration, and you can build either layer threes or build another layer one, and this is like super interesting, I think. But for the time being, we're going to focus on privacy. There is a lot of design space, a lot of need for application using privacy right now. So yeah, I think that this will be like a good point to get started. Just like a last note about scaling, you may think like, okay, I thought that CK was only about privacy. So why is the case that you can also do scaling applications? And the answer like is very clear. We can go back to this phrase, like you can prove something without revealing all information. Like in the privacy applications, you can prove that you have a valid vote, without revealing who you are. You can prove that you want to make a transaction without revealing the destination, for example. You can prove that you are going to post, you have a post because you're a valid token holder without revealing uh, which token holder you are in a social media application. And it's the same for a scaling application. From the layer 2 perspective, for example, scroll perspective, you can prove to Ethereum that you have all these transactions, but they are valid. You have bundled them without revealing all the transactions. So it's like the layer 2 is like doing like privately passing transactions to layer 1 just to make it cheaper and faster. So yeah, that's why if you were interested in that. Okay, let's go into focus into privacy applications. So you already know a little bit about Solidity. You already know how to build your smart contracts in Solidity. So these are normal functions that you may want to write. But if you notice there is like a keyword that I put there that is not possible on Solidity. So, for example, you can have like a cast vote or mint NFT or transfer from. These are like very normal use cases of Web3. But what you can't do is have like these private parameters on your functions. So, for example, if you want to cast a vote and you want to keep the voter private, you can't do that. You can just put like address private voter, and 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 yeah, it won't work. If you want to mint an NFT, the same. If you want to mint it to someone else, or you want to transfer some tokens, NFTs or ERC20 tokens, if you and you want to make the transactions, like the destination of the transaction private, you can't do that. It's not possible on Ethereum. Why? Because Ethereum is deterministic and Ethereum is public. Everything is public by default. Why? Because you have to verify everything. So when Ethereum was created, we didn't have in mind CK. We didn't have in mind privacy. We didn't know it was possible. We actually we thought it was impossible because it would require too much computation. There is a famous video from Nick Szabo. Nick Szabo is like a super, like he's a very knowledgeable and person in Bitcoin. He mentioned that zk, it was a great technology, but it's just impossible, computationally impossible to create. But now this is possible to do. Like this that I'm showing here, having private parameters is possible to do with the help of zk. And it's not as easy as I'm writing it here. It's not as easy as just putting private on your on your smart contracts, and I'm going to explain why in a moment. But it's not that hard either. So let's go and see what you need to do it, and also like go through an example to do it. So this is what you need to have in order to create a privacy applications. You need three components, and two of them you already know it. So yeah, we're going to see yeah, what they are. And of course, you need a web applications or a native application, mobile application, whatever interface you prefer. You need an application so the user can interface with your, yeah, with your app. And you also need a contract that you can write it in Solidity, for example, and that's what you already know. But you need something new. You need to also have a circuit. So what is a circuit and how to build one? Okay, in this case we're going to have like this combination. We're going to be building on this workshop a application that combines. We're just going to use vanilla JavaScript with Web3.js for your front end to interface with your contract. You can do the normal API calls with an RPC. What you're already used to is exactly the same. We're going to use Solidity to deploy on chain, but we're also going to add a new component, and the new component is Noir. In this case, Noir is a circuit language which is super similar to a programming language, and I know you will feel very familiarized with it. When you see it, you will see that it's not really that hard to understand. You just need to know a couple of tricks that I'm going to show you, and you will be set to get started. And also to mention, this combo that I mentioned here is not the only combo, of course. Instead of Noir, you can use other circuit languages. We call them zkDSL, zk domain specific language, like Circom. Noir and Circum are the two biggest ones. They are not the only one, but these are like the two that will recommend you to get started. My recommendation right now is to get started with Noir. There are some live applications using it, and also it's very easy to understand. The Circom has more applications than Noir, more battle tested applications. There's a lot of TVL, a lot of users using circuits done in Circum that hasn't been hacked. So that's very good, that's very secure. But Circum is very hard to understand at the beginning, just at the beginning. So my recommendation is that you get started with Noir. Also, like we're going to use Web3.js, but you can use like React, Angular, Vue.js combined with Ether.js VM to handle the Ethereum logic on your front end. And of course, instead of Solidity, you can either use Viper, but I wouldn't recommend using other language than Solidity for zk, because all major DSLs, such as Noir and Circums, are compatible with Solidity. So I would recommend you to stick with Solidity for this one. For the other ones, you can pick whatever you want. Okay, one last thing before going into the hands-on tutorial. So when you are writing a circuit, and we're going to see a circuit in a moment, you will have to think a little bit different on what you are trying to do. So when you're writing a function, like a normal function, either a Solidity function, a front-end function, a backend, a whatever you do, you think of function like functions in any type of programming language. You can think of them so as you can have like parameters, like in this case, x and y are parameters to your functions, and then you have the return values. So input, process, output. That's how we think as developers. In zk, you have to think a little bit different. When you're writing a circuit, you will pass as parameters your actual parameters, your inputs and outputs. So your inputs and output both are parameters to your circuit, and this circuit, it will produce a proof. So it's a little bit different how you think about, but the syntax is very similar. You will see it's not very different about what you're used to. Also, just to go a little bit ahead and talk about it, is like this proof. What do you do with this proof? Okay, this proof, you grab it and you verify it and compute it on Solidity. So that's how your circuits and Solidity knowledge combine, and so you can create privacy applications. Okay, let's start with this one. So I'm going to give you a second to scan this QR code, and this is a getting started guide that I wrote for Noir. Very simple, just a minimum code. I'm going to do it with you guys here in a second. So yeah, just go ahead and grab that link, and yeah, just can just follow installing Noir and some yeah, you're going to need to start to things like Noir and Barenberg, and I'm going to do it myself. Yeah, with you. Okay, so I'm going to so this is the guide, very simple guide. Also, at the end of this presentation, I'm going to link you to some resources, the official documentation where I got this from, but of course the official documentation is a little bit more extensive and cover more things, so you can go and check those details later. Okay, so I'm going to actually going to send this here. Okay, so and I think I'm going to do this a little bit bigger so you guys can see. Okay. Just make it a little bit bigger. Okay, that's better. Okay, so here I'm going to, once you have installed these libraries, noirup and bbUp, I'm just going to check the version. Oops, Nargo. So with the noirup command, you will install Nargo. So this is the version that I'm using, and also the bb command for Varenberg. Going to explain that in a moment what the difference is. Okay, so once you have done install with these commands, we're going to create a new project. We're going to create a new project, cd into it, and execute this nargo check that is going to basically compile it and build a file called prover.toml. So in here you have the project file, which is nargo. You can set the name, also you can install some dependencies, but the most important part here in source is the main.noir file. And if you can install like some linters so you can get colors on your code, but just so you know, this is a language inspired on Rust. So yeah, if you're familiarized with Rust, this should be very easy for you. Okay. So this is just a test function. This is the core of the circuit. This is the circuit. So in this circuit, this is a very simple circuit just to get you started that receives two parameters, x and y, and it makes an assertion. It checks if the parameters are different. So there is one very important thing in this circuit is that the y parameter is public and the x parameter doesn't have the pub keyword. So that means it is private. So x is private and y is public. So you here is that's how you can like have public and private parameters. So in here, going back to my presentation, so here in your circuit you can have different parameters, and one of those can be public and the other one can be private. So that's the different things. That's how you can handle them. So let's see how this connects to your knowledge, that the knowledge that you already have on Solidity. So let's see. Let's continue with this tutorial. We're going to generate a proof of knowledge that I know two numbers and one is different of the other one, but I'm not going to reveal one of them. I'm just going to reveal the other one. Of course, this is not like a practical application. That's why at the end of this workshop, we're going to do something more practical. We're going to do voting application. Also, I'm going to link you to other examples that you may find interesting. Okay, so now we're going to generate a proof. So on the prover.toml file, you can put here two numbers, 1 and 2. You can put whatever you want, as long as the numbers are different. If the numbers are equal, you won't be able to generate a proof. And then we're going to compile, nargo compile, and this is going to generate a JSON file of like the like some artifacts of building. Now we're going to execute. Okay, so basically, we were able to generate this file that was able to produce like some sort of pre-proof. Like we were able to check that this was indeed possible to generate a proof, but we haven't generated the proof yet. This with the bb command that we just installed, we are now able to generate a proof. Okay, so here you go. So the proof was put in this proof file. So let's see how the proof looks like. It's just a bytes, just a lot of bytes. Here you can see just a lot of numbers and numbers of bytes. And yeah, this we're going to see like how to serialize it in a moment. Okay, now we're going to do something very interesting. Just put these two commands that based on the files that were generated, we're going to generate verifier.sol. And this is something that you may be familiarized with. So take a look at this verifier.sol file that was generated, and you may be more familiarized with this because this is a Solidity smart contract. So a Solidity smart contract was generated, and this Solidity smart contract is able to verify a proof. So we created a proof here, and if we pass it as parameter to our smart contract that was generated specifically for our circuit, you will be able to verify if it's true in case it returns true. So how does it work? So let's go here. Now let's go to, you may be familiarized, of course, with Remix for deploying smart contracts. And what we're going to do here is that we're going to create a new file, my verifier.sol. I'm going to paste it here. I'm going to compile it. There's one trick for compiling it, and I put it in the guide in the gist, is that you will get this error that this is too big. Basically, this, as you can see, this was automatically generated and is able to check. This contract is able to generate your proofs, but it's just too big. It won't fit in an Ethereum block. It's too big. So we need to optimize it. And to optimize it, you go here to advanced configuration and just click here, optimization 200 runs, and that will be enough to get this blue check here. Here you go. And now you're able to deploy it. And you're going to pick here honk verifier, the honk verifier. This is the backend that reads. So zk has different backends, different proving system. You have Plonk, honk, Grad16. There are many. In this case, we're going to use honk. And you can pick either the virtual machine, or you can also like deploy it using like your normal wallet or whatever. I'm going to just deploy it in the virtual machine. And now you have two things. You have you have a function that is called verify. It's a Boolean function, returns true or false, and it receives two things as parameters: a proof and some public inputs, an array. So as you remember, our proof is this one that looks super weird because it's just a lot of bytes. And also the public params are x. Remember, sorry, y is public, x is private. So um, this is you can have like many arrays, many public parameters, and in this case we only have one, so we're going to need to pass it. And in order to do it, I added here a script. So just go ahead and create a new file, serialize proof, and just paste it here. And we're going to run this command, and it's going to serialize the proof in a format that basically we can pass it very easily to Remix. That's why we added this script. So this is the big proof of computation. You can see it's very, very large. So we're going to copy and pass it as the proof here. And then this is the public inputs. There's only one, and it's the number 2. There are 32 bytes array for the number 2. Remember, this is y. This is y. This is the y that is public. So here, x is not passed to the smart contract. Y is passed because it's public. And y, I set it to 2. So here, I'm passing the 32 byte value of 2 to my smart contract. So let's see and check it. Let's go here, just to remove this comma that, okay, my script was not too good. Also put pass it as a string, and let's compute it. And it returns true because it verified that my proof was successful. And if you try to modify any tiny value from here, you won't be able to verify the proof. If I pass 3 here, it's going to revert. So this won't work. So yeah, this is how like a circuit communicates with your Solidity smart contract. So the normal flow is that you create a circuit, generate a Solidity verifier, deploy the Solidity verifier, and then just go ahead and create your own logic as you're used to on your Solidity smart contracts. And you have this verify function that's able to check the proof, also and play around with the public inputs, because you have public and private inputs, and you can have some computation done only here on your circuit, and you can have privately here, and you can have some computation done on Solidity. It's the computation that's going to be public, so you can play around with these things. So let's go back to our presentation and see a more advanced guide. So as I told you before, we're going to do a voting application. So what we usually do, you know that in Ethereum, we have DAOs, we have governance, we do voting, we vote on protocol upgrades, for example, on Scroll. When Scroll wants to launch a new version of the protocol and wants to upgrade and do new cool features, we go to a governance process. People talk with tokens of Scroll vote, and only if the vote is successful, it will pass. Or also you can manage treasury. DAOs have treasuries. They have some money on smart contracts, and they can vote to decide what to do with that money. So yeah, you can have different types of application. You can also do, for example, I don't know, elections. Like you in Egypt, you can maybe in the future vote for the president or for the mayor of your city, and you can do that on chain. But of course, there is a problem: is that right now all the votes on Ethereum are public, and you don't want that, because you can then do a coercion, and you can like force people to vote or you can see who voted for which. Is That's not good for democracy. So we can of course fix that with zk. So how would that work? So instead of passing a vote to a smart contract like we're used to do in Ethereum, instead of doing that, we pass a proof. We don't pass a vote, we pass a proof to a smart contract. And what do we do in this voting smart contract? What do we do with that proof? We pass it for verification to our verifier smart contract. We have a circuit that verifies votes, and then so the user passes the proof to the smart contract, and the smart contract checks if the proof is valid by checking with the other smart contract generated by our circuit, and then the proof is sent back to the smart contract. And if it's correct, we count the vote. If it's not correct, we don't count it. So, and also, like, the other question is, okay, how do we make sure that this is a valid voter? Like, if anyone can produce a proof, okay, we can, that wouldn't be fair. So what we're going to do here, and this is like a very specific keyword, but I'm going to explain what that means, is we do a proof of inclusion. So we're going to prove that you are part of a group without revealing which member you are. You're going to, like, basically proof of membership. Going to prove that you're one of the list without revealing which one on the list you are. And this is going to get a little bit more advanced here. And don't worry about it if you don't understand everything. Like, of course, you can also ask questions about it, or if you're more interested about it, you can contact me after this workshop. But yeah, also for the sake of time, I'm going to advance a little bit faster, but don't feel discouraged if you didn't understand like a specific part of this. If you're a developer and you're already building Solidity, as I said before, you just have to learn a few tricks to just get started building on zk. And one of these tricks is the one that I'm going to explain here. That is the proof of inclusion. So you have this, which is a list. So you have, for example, A, B, C, and D, and you're going to prove that you're one of these by just just making a CK proof, a seeker like seeker inclusion proof that you're one of the list. So here I have another example. This is a repo, a GitHub project. So feel free to just clone it in the README. You can go on the step by step on how to use it, and yeah, we're going to start using it now. So what we're going to do now is that I'm going to showcase the demo. Then I'm going to start like little by little, and depending on how much time we have, going to go deeper and deeper and deeper into explaining how it works. So okay, let's go ahead. And okay, so here I have let me check. Here I have the project. This is, of course, a very simple project. This is something that I vibe coded on the weekend. By the end of the workshop, I'm going to leave you with some links with some projects that you may be more, that you may want to look for, like, and be more familiarized with them, because they're more organized than this one. But I think I did this specific example for this, so you can understand uh, the techniques used here better. So let's see. Uh, like, for example, here I already have a proposal of a vote. Hey, let's eat pizza is the proposal with the ID 0, and then it has already one vote. So let's go ahead and put another vote. So I'm just going to explain later what is this tree is like, and we're going to see what it is. But for example, here I'm going to say, okay, I'm going to vote. I am the voter number 2 with the private key number 2. No one knows my private key, only myself. and I'm going to vote for the proposal ID 0, and I can vote for or against. I'm going to vote for. So I cast my vote. Here it is generating a proof. And yeah, it just generated a proof, and then MetaMask pops up. Oh, by the way, the latest update from MetaMask has not been working really good, so I would recommend this something else. I'm using Ravi, having good results. But yeah, just my recommendation is if you're developing on zk, yeah, don't use MetaMask. If you're using MetaMask, you can try it right now, and it may work. But um, oops, I think it reverted. I'm not sure why. Let's try again. Yeah, my recommendation is just um, not to use um, MetaMask. It's being like super faulty lately. Okay, so when that finish, I don't know what that failed, but here it should be 2 votes for. And this is like my example application. Very simple application, but yeah, we're going to start explaining what do you need to build something like this, because here you can see like the vote was successful. Now I have 2 votes, and it was counted. And if I try to vote again, I won't be able to, because my vote was already submitted. So that's another trick that you also need to learn. Because when you're building private application, you have to understand like the implications and the limits. Because, for example, if you're building like a trading application, like Uniswap, for example, Uniswap, and that you have liquidity pools, and you can like swap one token for another. The problem is that how do you know how many tokens are on the pool? How do you know the price if you don't know the amount of tokens that are being swapped? So there are some limitations on what you can do just because of like pure like logic on what is possible and what's not. But there is like a huge design space on things that you can do. So here, of course, the vote failed because yeah, I already voted. So the application here, of course, you can count the votes publicly. You have a list of voters. Only these voters can vote, and when they submit a vote, the vote itself is public, but the voter is private, so you don't know who the voter is. Okay, so let's see like how is this possible, how this application, what is built, and what is this thing that is here. So let's go like one step at a time. So the first thing that we need to understand is hashing functions. So hashing functions are super important for um, blockchain in general. So you can, the most famous hashing function is Keshak Online. Let's see. The most famous function on Ethereum is the Keshak 256. So the Keshak function allows you to, for example, based on whatever input, an output is produced. So the thing about hashing function is that this is A and this is B. From A, you can go to B, but from B, you can go to A. So every time that I put the same number here, is going to produce this output. But this output doesn't reveal any information about the input. So when you create a new wallet for the first time, and um, you 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 put like your 12 words, your 12 word private key, it will produce a publicly based on those 12 words, right? So that's the way how Ethereum private keys are made, because every time that only you know your private key, your 12 word, your mnemonic, your private key, whatever. So only you know it. No one else know it. So from your private key, you can prove that you know it and generate a public key. Your public key is, of course, your address, this one, right? This is your public key, this one. But from your public key, you can't know the private key. So from A you can go to B, from B you cannot go to A, and from your private key you can go to your public key, but from your public key you cannot go to your private key. So what we're going to do here is that we're going to build this. This is called a Merkle tree. This is another new topic that I'm going to explain. Based and on it's a tree, a binary tree, or you can have like n tree, whatever you like. This is a tree, and the leaves of the tree are the public keys, and then you basically hash all the leaves and produce the root, and the root is going to be stored on the smart contract. Okay, so let's go ahead first and just create a tree of public addresses. So this is something that not is not only used in zk, it's also used, for example, in NFT airdrops. You can have like a Merkleized NFT airdrop if you can like prove that you're part of a Merkle tree by using this technique or this type of tree that is very specific called Merkle trees. So here I am going to build, for example, a tree, very simple tree of 4 leaves. You have like the leaf A, B, C, and D, or like 1, 2, 3, 4, and then I have um, this function that can compute the Merkle tree. And as you can see here, I'm computing this Merkle tree because if you hash 1 and 2, you get this one, and if you have 3 and 4, you get this one, and if you have this and this, you get this one. So that is a Merkle tree. So let me explain it better. For example, I'm going to use. Oops. Okay, so this is a Merkle tree, and this is very important to understand, and it's not very hard. I'm going to explain it here. So, oops. Let me see. Hmm. It's going to try it. So here you have 1, 2, 3, and 4. So you have 4 elements, and you want to make a Merkle tree based of this. So what you're going to do is that it is a binary tree where this is the hash of 1 and 2, and we're going to call it this. I don't know. We're going to call this X, and this is the hash of 3 and 4, and we're going to call this Y, and then we hash this, and we get the root, and this is going to be the hash of X and Y. So this is a Merkle tree, and this is something very useful in blockchain. Actually, we use it in many places. Yeah, I think this is you can see like how a Merkle tree works here. This is all of it. This is how it works. Just you hash like sibling with your siblings, and then your uncles with their uncles, and the uncles of your uncles, until you get to the root. This is the root. So the root, it can serve to many things. So for example, in Ethereum, all 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 variables, everything is stored in a Merkle tree like this. Actually, a Merkle Patricia tree is a little bit different, and it's going to be changed in the future probably, but it's the same idea. all the variables from all the contracts, all the token balances, all the NFT owners, all the votes, everything is Merkleized. And the root is what is stored in the block headers. This is also using for different things. In our case, for our voting application, what we're going to do is that we're going to have the list of voters, and then we're going to hash them and generate the root, and the root is going to be stored in a smart contract. And when you submit a proof, a public parameter of the circuit is going to be the root that you're computing, and it's going to be compared with your smart contract. And you can see the smart contract here. Um, Here, this is your voting application. Oops. Okay, I don't have the colors set up, but please bear with me. So here is the voting application, and as you can see, when you cast a vote, you send the proof and the public parameters from the proof. And very importantly, you store the proof of the Merkle tree in the contract. Why? Because you want to check that the that the proof matches with the Merkle tree on your smart contract. So in here, what we did is that first, um, I just generated 4 public keys for based on 4 private keys. Of course, this private key is too simple, just a number 4. You shouldn't be using that. This is just an example. But from here, you have like generated these public keys from the private keys, and then from there you compute the Merkle tree. This number gets stored on the smart contract, and then when you create a circuit, this is the circuit. Okay, we don't have too much time now. I'm going to go um, a little bit faster, and also we can leave some time for question at the end. But the main idea is that you on your smart contract, you prove that you're part of the list by making this by proving that you're part of the root. As you can see, the circuit is very simple. You just it's very not simple. I think it's short. uh, and but once you understand, it becomes simple. At the beginning, I think for me it was very challenging to understand. um, so you generate a proof. You pass as parameter the root of the tree, then which element you are in the tree, the element 1 2 3 4 5. You pass your private key, and then you pass what we call a hash path. So basically all the minimum amount of elements that you need to reconstruct the tree. And then very interestingly, you can pass some extra public inputs. So in this case, we're going to pass the proposal ID, and the vote. So the proposal ID is 0 1 2 3, depending on the proposal that you want to vote on. In here, we voted for the proposal 0. Is in here. We voted for the proposal 0, which is Let's Eat Pizza. And the vote 0 for or 1 and 1 for against. Something, I think it was that. So you can pass some extra parameters, and of course these parameters are going to be public because they're going to be you will be able to read them from your smart contract, and you will be able to interact with them. So let's look which are the public parameters. Here it's the root, because you want to compare that the root that you passed to the circuit is the root that was passed to the smart contract. The proposal ID, because you want to be able to know which proposal ID you vote for. You vote for and against. And then there's this a little bit more advanced. You don't need to understand it right now, but I'm going to explain it also. This is the nullifier. We pass the nullifier as a return value. The nullifier is a mechanism that allows you to protect you from double votes or double spend, double action. So you can mark them, and you won't be able to do two actions twice. On the smart contract, when you cast a vote, you will receive the public inputs. So the public inputs come from your circuits, right? So it's the root, the proposal ID, the vote, and the nullifier. So here you can store it like the root, proposal ID, vote, and the nullifier. And then you can play around with it in Solidity. In here, it is a voting applications. So we are going to handle the votes. Like we have a hash map of proposals, and the votes which you're just going to 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 just update based on your vote, your type of vote. And that's the idea. Yeah, my idea with this application is not to to so you can understand specifically, um, you can understand specifically voting applications, but just so you know that you using Solidity, you can have private parameters, and you can have some computation done, and this is also very important. The computation has to be done on the browser, on JavaScript, because if you send this for computation, your private parameters to a backend, your application is not private anymore. So everything has to be computed on your computer using JavaScript, like in this example. And then once you form a valid proof, you can send it on chain, and the parameters will be hidden from anyone. Only you will be able to see. Just like we're only able to see our private key, you can build application that you can choose actions, and you can compute them, and only you will be able to see them. So yeah, there are many things we can talk about this, but let me just leave you with here at the end. I leave you with some resources if you got interested in building CK applications. Um, you can go to the Noir official documentation. You can go to my Wasm to the official Wasm proof example that basically Wasm is making proofs on your browser. Basically, Wasm is JavaScript, basically, kind of, and how to do a proof with JavaScript. Very important, as I mentioned, because you will need to do it to keep application private, because you don't want to send information elsewhere. Also, the official contract verification, like contract, yeah, basically connecting a circuit with a contract on Ethereum. And also an example that I did myself. If you want to have like an end-to-end example, I didn't find for Noir any end-to-end examples, so I did one myself. So here you can check it. It's a very simple hangman game, and yeah, you can check it out so you can know. You can also check this CK voting application, but I think it's too many things happening on the screen. I just want to show you like a little bit of what happened behind the scenes, a little bit of what you need to understand. But if you want to like actually go and read the code and understand, I will recommend you this hangman tutorial. Yeah, I think that if you still have some time for uh, for questions, I hopefully didn't go too fast. So feel free to ask any question. Yeah,
And
yeah. Go ahead, go ahead.
I just wanted to say, like, thank you, Castro, for the amazing workshop. We really appreciated the way you broke down such a complex topic, and it was very, very clear and engaging. We hope that everyone now has a better idea about ZK, and hopefully they will be building ZK apps on Scroll soon. If anyone has a question for Castro, you can raise your question right now.
Yeah, thank you. Hopefully, it wasn't too complex for our first workshop, but yeah, usually it takes time to understand, but it's not really that different from what you already know. Um, you have to learn these circuit languages. You have to connect them with Solidity, but yeah, feel just it's not really If you put the time and dedication, you can build like very very interesting application. Also, I invite you to like something that I've noticed by going to different countries is that in every place there are different needs. So, for example, voting is something super important for us here in Latin America. Basically, we don't trust the voting systems. DeFi is something very interesting for the US and Europe. They are like financial hubs, and this is something that resonates with them, and they see a lot of issues that can be solved with zk. Identity on China is very important. So I invite you to also think about what type of application can solve a local need in North Africa and the Arabic region. So just think about it, like, and don't be afraid to to yeah to trust in your instinct and and the things that you're seeing. And of course, if you want support to building your application, there is a scroll open again, some commercials about scroll open. So feel free to apply or ask me, or connect with maybe if or yeah, you can ask me like directly or through Omar or Karim. So yeah, are there any? I'm going to stop sharing now.
Yeah, let me share a QR code for the feedback if anyone wants to give a feedback on the session. We appreciate your feedback here. And does anyone has any question? Okay, so thank you so much.
Oh, there is
And
another, I think, raise his
yeah,
hand.
uh, yeah, yes,
Yeah, hello everyone, and thank you for the lecture. It was very important and very useful. My question is it possible by the time to get to work with the ZK even easier than you did you are writing your own script, I think, then I think there will be an easier tools by the time or not?
Oh, the script for generating the proof to be able to verify on solidity. You ask, right?
Yeah, yeah.
Oh, yes, yes. Yeah, I didn't mention it, but on the second example, or on the if you want to, yeah, there are tools for it, do it, and you don't have to use a terminal for doing it. And of course, you shouldn't ask your user to put something in the terminal or to compute it in a server because it won't become private anymore. So you need to do it in JavaScript, and it's very important to do it in JavaScript. So in general, I'm going to type here in the chat. The keyword that you need to work for it is WASM provers. That's general, like how you will look for it. And in terms of examples, the CK voting application that I shared, use it. And if you want a more concrete example, you can see the official WASM example from, yeah, this one. Um, official, yeah, here. So this example is the official one from Noir. There's also some example for Circom if you want to use Circom instead of Noir. Uh, and also like I mentioned, the CK application, the voting application that I showed, use what is described here, because it's important that the proofs are generated in JavaScript. It's not only a user experience thing; it's also a security thing and a privacy thing that only your browser should be able to handle your private inputs. Yeah, yeah, great question. It's something that I didn't mention. Yeah, thank
Thank
you.
you very much. I have another question then. Except for the voting systems, what other application can we use in real world assets or real estate, maybe?
Yeah, so you can have like specifically in real world assets, well, like first the applications that are already working right now, and there are like yeah, just proven that CK is ready to be used. Of course, number one is Tornado Cash. Tornado Cash is private DeFi, and it's a mixer that everyone can see who deposit. No one can see like no one can link the withdrawal from the depositors, and you can think about it also like in terms of, for example, real world asset. I haven't seen like a real world asset application with privacy enabled yet. I think that will make a lot of sense. So what can you do with it? So at the same time, for example, you have your real world asset represented as an ERC20 token or as an NFT. Then you can do the same as in Tornado Cash. You can mix it. Basically, you can deposit in a contract and then withdraw it, and no one will be able to link you the depositor with the withdrawal. And also, while it's in this privacy mode, we also called it shielded mode. Shielded mode. So you have like the public mode and the private mode. The public mode and the shielded mode. While it's in shielded mode, you can also play around with it. You can do, for example, deposit in a privately, deposit in a
Maybe
um,
we can give a
mhm.
social maybe we can give them social uh, social, I don't know what they call for habiting, for inhabits, social inhabiting, like Vienna or Singapore, and don't know who is the owner or who deserve this property. Maybe
Yeah,
I
like you can prove, for example, you can take a loan, for example, privately, because you are proving that you're one of the owners. That can basically make sense. You can also make some census, for example. Sense.
social housing. It's called social housing. Maybe we give
Oh,
social housing
mhm.
to the people without knowing them, who
Yeah, yeah, yeah,
deserves
yeah.
and who not. You think I think you know you understand me now.
Yeah, yeah, I understand. I see. Yeah, now I understand. Yeah, yeah. Also, like, I guess that's also a little bit related with universal basic income, for example. You can send some deposit to different others, or you can be able to claim if you prove some things about yourself. And there are many projects like live projects that are coming now. For example, there is CK peer to peer that you can make peer to peer transactions like help with CK or CK email that you can prove that's something very cool that you can prove that you are the owner of an email. For example, I can prove that I have like a scroll.io email, but I won't reveal that I am Ahmed. So you can do different things. Yeah, I think the most use cases right now are in DeFi, social media, votes. I think right now the industry, like I think it's moving towards identity, but yeah, there are many use cases. And as you mentioned, like real world assets, I think in real world assets, it's super related to what everything on with what like everything that's happening on seeking on DeFi right now, private DeFi.
I think we need to find out. We are just in the beginning.
Yeah, yeah, yeah. I agree. Yeah, it's just the beginning, and the tools I just right now are starting to be more accessible for developers. Like these WASM provers, they didn't exist like before. Like even a year before, they were like super like harder to use. So yeah, I think we need more more ideas, more application. So yeah, if you want to, yeah. So I think that's all the questions. Yeah, thanks
Yeah.
everyone for
Thank,
joining.
Yeah, thank you so much for the awesome workshop. And anyone else has any question? Okay, that's it. And thank you so much, Castro, for the amazing workshop.
Thank you. I hope to see you soon.
Thank you. Bye.
Bye bye.